Welcome to the course analysis 1. In this lecture, we study completeness property. So intuitively, completeness means no gap. Or in other words, no missing point. Missing point in R. So where R is the set of all reals, this contrast with Q, Q is the set of all rationals. So here we have gap at every irrational point. Every irrational point. So there exists some equivalent notion of completeness or notions or forms. For example, quasi-completeness, so it says that every quasi-sequence converges at some point. Okay, so we may regard completeness as an axiom. And using this axiom, we may prove quasi-completeness as a theory. Okay, so set up all reals are, this is a field, and we have order relation in R, and this is complete ordered field. So in a moment we will define everything, and one more thing I would like to mention. So completeness is also known as least upper bound property. So completeness property is also known as least upper bound property. Well, let us start with a few definitions and notations. Definitions and notations. N, this is equal to 1, 2, 3, and so on. This is called a set of all natural numbers. Set of natural. Set of all natural numbers. And second thing, this is Z. This is equal to 0, plus minus 1, plus minus 2, and so on. This is set of integers. Third item is Q. This is equal to P over Q, where P belongs to the set of all integers and Q belongs to set of all naturals. And one more condition, that is GCD of P and Q. So greatest common divisor, GCD of P and Q, this is equal to 1. That is, P and Q, they are relatively prime or co-prime, and this is called the set of all rationals. Set of rationals. It is a fact that Q, the set of all rationals. So this is a field, and here we have an order relation. Okay, and this is ordered field. So we will define what is order relation and what is field and what is ordered field. Everything we will define in a moment. So first we define what is field. So let us define field. So a field, F, is a set with two operations O1. This is first operation called addition, and it is denoted by plus. So this is called addition, and second operation O2, this is denoted by dot. This is called multiplication. This is called multiplication, which satisfy following so-called field axioms. Field axioms. So these are the field axioms. A, axioms for addition. So here we have 5 axioms. A1, this is closure. It says that x plus y belongs to f for all x comma y belongs to f. Okay. And this is called closure. So if you take x, any x and y in f, so their addition x plus y is in f. Second axiom, this is called commutativity. That is the binary operation plus, this is commutative. That means x plus y equal to y plus x for all x comma y belongs to f. The axiom for additions. A third axiom is this is associativity. It says that x plus y then plus with z, this is equal to x plus y plus z. This happens for all x comma y comma z belongs to f. And fourth axiom for addition, this is, it says that, so this is basically existence of additive identity. Existence of additive identity. It says that there exists an element denoted by 0 in f such that x plus 0 equal to 0 plus x equal to x for all x belongs to f. And 0 is called additive identity, called additive identity. And axiom 5, this is existence of additive inverse. It says that to each x in f, there exists an element we denote it by minus x belongs to f such that x plus minus x equal to minus x plus x, this is equal to 0. And minus x is called additive inverse to x. So these are 5 axioms for addition. And next set of axioms, these are multiplicative. So axioms for multiplication. Axiom for multiplication. So axioms for multiplication. Here also uh, we have five axioms for multiplication. First one M1. This is also called closure. X times y belongs to f for all x comma y belongs to f. So multiplication is closed. So f is closed under multiplication. That is for every x comma y in f, x times y, this is in f. So multiplication is closed in f. The second axiom for multiplication, that is also called commutativity. So that is basically multiplication is commutative. Okay, into so x times y equal to y times x for all x comma y belongs to f. And associativity M3, third axiom, x times y then multiply with z, this is equal to x times y times z for all, this happens for all x comma y comma z belongs to f. Okay. This is the third axiom for multiplication. And fourth axiom for multiplication, that is existence of, so here it is multiplicative identity. Okay, sorry, this is M4. Fourth axiom. So it says that there exists an element we denote it by 1 in f such that 1 times x equal to x times 1, this is equal to x, and this happens for all x belongs to f. And 1 is called, this is called multiplicative identity. Multiplicative identity. The fifth axiom for multiplication says that to each x in f and x not equal to 0, where 0 is additive identity, so minus 0, there exists an element, we denote it by x power minus 1 belongs to f such that x times x power minus 1 equal to x power minus 1 times x, this is equal to the multiplicative identity 1. And this x inverse, this is called multiplicative inverse to x. The multiplicative inverse to x. And Also, addition and multiplication satisfy another law, that is distributive law. It says that multiplication is distributive over addition, and it says that for all x, y, z, for all x comma y comma z in f, x times y plus z, this is equal to x times y plus x times z. So that is multiplication is distributive over addition. So this is distributive law. So that is a field f is a set with two operations, plus and, so that is addition, and dot, that's multiplication. And addition satisfies these five axioms, and multiplication also satisfies this five axiom. And 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 addition, multiplication is distributive over addition. So for example, Q is field where uh, plus is usual addition is plus, and usual multiplication of rational, this is multiplication. Okay, so this is a field. Now, now we define ordered set. So before going to the definition of ordered set, we prove a theorem called no existence theorem. So before going to the statement of no existence theorem, so let us consider a picture. So let us consider a triangle. So consider this triangle, so right angle triangle, and this is the right angle, 90 degree, and let's say this has unit length, and this is also base has unit length, and let's say the third side has length r. Okay, so by Pythagoras theorem, what we have, r square equal to 1 square plus 1 square, this is equal to 2. So r square, this is equal to 2. So r is some real number. Okay, so r is some real number, which is the length of this side. Okay, and we show that r is not rational. Okay, so let us state as a lemma. This is called no existence theory. It says that there exists no rational r such that r square equal to 2. So this is a simple statement, and this lemma leads to the irrational numbers, not this lemma leads to the irrational numbers. For example, if you consider a sequence 1.4, 1.41, 1.414, and so on, 1.4142, and so on, this converges to some real number which is equal to root 2. Okay, so now let us prove this lemma. The proof of Yeah. The proof is by contradiction. The proof is by contradiction. So assume that assume that there exists a rational number r equal to p over q belongs to the set of rationals such that r square equal to 2, that is p over q square, this is equal to 2, and this implies p square equal to 2 times q square. And therefore, so this is even integer, and therefore p square, that is also even integer. So p square is even integer, that is 2 divides p square, and 2 is prime, so therefore p, so 2 divides p, that is, this implies p is even integer. So p is even integer, so therefore therefore there exists some m in z such that p equal to 2m. Okay, so there exists m, some integer such that p equal to 2m, because p is even. Now we replace p in this equation, then we get 2m square, this is equal to 2q square. This implies q square equal to 2 times m square. So by similar argument, we conclude that q is also even. Okay, q is also even, and similarly there exists n in the set of all integers such that q equal to 2n. Now note that GCD of P comma Q, this is equal to GCD of 2. So we replace P by 2m and Q by 2n, so which is equal to GCD of 2m comma 2n. Okay, so this is equal to 2 times GCD of mn, and GCD of mn, this is greater than or equal to 1, so this is greater than or equal to 2, but p over q, that is rational, and we have GCD of p and q is equal to 1. So this contradicts that. So here what we get, GCD of PQ is greater than or equal to 1, which contradicts that GCD of PQ, this is equal to 1. Okay, so therefore this completes the proof. And now we have an exercise over here. So let me change the color. Show that between every two rational numbers, there exists another. That is, if you take two rationals R1 and R2 such that R1 less than R2, then there exists another rational R such that R1 less than R, and which is less than R2. Okay. So now we define ordered set. ordered set. So here is the definition. Let S be a non-empty set and order on S is a relation, and this relation is denoted by this, and we read it as less than. Okay, a relation less than such that has the following properties. That has the following properties. The first property is if x comma y belongs to S, then exactly one of the following holds true. What are the following? Either x is related to y, that is x less than y, or x equal to y, or or y is related to x, that is y is less than x. So one of this, exactly one of these following holds true. The second condition is this relation is transitive. That is for, so if x comma y comma z in S and x less than y less than z, then x less than z. That is, if x is related to y and y is related to z, then x is related to z. That is this is transitive. And so this is a definition of order. So the next definition is ordered set. So this definition is very simple. A set or a non-empty set equipped with an order. So an order means a relation that satisfies these two conditions. Okay. So a non-empty set is equipped with an order less than is called an ordered set. And we denote it by pair S and this relation. Okay, so this is the notation for ordered set. For example, set of all rationals and this relation. This is ordered set. And we have some notations. X less than y is equivalent to write y is greater than x. Okay, so this symbol is called greater than. Second, x less than or equal to y. This we mean by this we mean that either x equal to y or x less than y. Okay. So these are the notations. Now we defined bounded sets. So we start with an ordered set. Let s comma less than b, and ordered set and e some non-empty subset of s. So e not equal to empty set. Then we say that the definition starts here. So definition, we say that E is bounded above if there exists, or more precisely bounded above in S. In S, if there exists some element beta in S such that x less or equal to beta for all x belongs to E, and E is called bounded below in S if there exists some element alpha in S such that alpha is less or equal to x for all x belongs to E. So this is the definition of bounded below set, and this is the definition of bounded above set. Now we say that E is bounded. E is bounded if E is both bounded above and below. So E is already written here. So E is bounded more precisely bounded in S if it is means E is both bounded below and bounded above. So here let me write so here beta, so such a beta satisfying this inequality, such a beta in S satisfying this inequality we call an upper bound of E. Such a beta is called an upper bound of E, and similarly such a alpha is called a lower bound of E. So if S is bounded below and alpha belongs to S satisfying this condition, then alpha is called a lower bound of E. And we say that such alpha beta, so E is bounded below by alpha and bounded above by beta. Okay. So, well, now we defined what is LUB, the definition. So, least upper bound. So, now we define what is least upper bound. Let non-empty set not equal to E, which is subset of S, where S is ordered set. Suppose E, let E be bounded above. Suppose there exists beta in S such that the first condition is beta is an upper bound, is an upper bound. So first of all, upper bound, beta is upper bound of E, and beta should be least upper bound. That is, if gamma less than beta, where gamma is in S, then gamma is not an upper bound of E. Gamma is not an upper bound of E. That is, suppose this is beta. If gamma, so if you have gamma somewhere here, that is less than beta, then gamma is not an upper bound of E. That means we have some element which is greater than, so some element we have here, so which is greater than gamma. Okay, so that is least upper bound means it is an upper bound and it is least upper bound. So the first condition says that beta is an upper bound of E, and second condition says that beta is the least upper bound. That is, if you have an element gamma, okay, which is less than beta, then gamma cannot be an upper bound of E. So we must have some element in E which is greater than um, gamma. Okay. Well, so let us complete the definition. So let E non-empty subset of E be bounded above. Suppose that there exists some beta in S which satisfies these two conditions, then beta is called the least upper bound of E, and denoted by supremum of E, beta. Okay, so similarly, greatest lower bound is defined. So definition GLB. So similarly, greatest lower bound is defined. So let me note it down. Similarly, greatest lower bound is defined. Again, so let us define it formally. Let non-empty set not equal to E and E is subset of S be bounded below. Suppose there exists alpha in S such that alpha is a lower bound of E. Alpha is a, first of all, this is lower bound, then it is greatest lower bound. So alpha is a lower bound of E, and it is greatest. So if there exists, if gamma greater than alpha, then, or in other words, let me write, if alpha less than gamma, that is if gamma is greater than alpha, then gamma is not a lower bound of E. Of E. Then alpha is called, then similarly, then alpha is called the greatest lower bound or largest lower bound of. Now we define LUV property. So what is LUV property? Here is the definition. An ordered set is less than is said to be have LUV property or least upper bound property, LUV property, if following is true. If the following is true. What is the following? If E non-empty subset of E is bounded above then it admits the least upper bound, then it has supremum of E in S. Okay, so this is the property, and an ordered set with this property is called complete. Okay, complete. So for example, R, this is complete. So that is, it has least upper bound. So exercise, we have an exercise here. Show that Q means the set of all rationals has no LUV property. So similarly, we can define GLB property, greatest lower bound property, namely an ordered set is said to have GLB property if every bounded below subset has a greatest lower bound. So here we have a mistake. So this should be S, subset of S. Okay, so similarly, one one can define GLB properties. So now question is what is or is, so what is the relation between LUB and GLB property? The following, so we answered this question in the following theorem. The theorem suppose S is an ordered set, then it has LUB property if and only if and only if, so they are equivalent basically. It has GLB property. Okay. Well, so before stop this lecture, we prove this theory. So here is the proof. So first we assume that S has LUB property. Assume S has LUB property. So S has LUB property means what? This means every non-empty subset A of S that is bounded above has a least upper bound. So by definition, okay. So by definition, S has least upper bound property means every bounded above set has a least upper bound. Now let B this is non-empty subset of S and which is bounded below. So this is an arbitrary subset of S which is bounded below. So what to show? To show B has a greatest lower bound. Okay. This is the forward part. So we define L equal to the set of all elements in S. B belongs to S such that B is less or equal to X for all X belongs to B. And note that this set is non-empty. Why this is non-empty? Because by our hypothesis, so we assume that B, this is bounded below, so it has a lower bound, okay, in S. So there exists some B in S such that B is less or equal to X, okay, for all X belongs to B. So L contains a lower bound of B, and B has lower bound because it is bounded below. So that's why L is non-empty. Okay, L is non-empty, and by the definition of L is bounded above, and every element in B is a, so this is every element in B is an upper bound. By definition of L, it is bounded above, and every element in B, and B is non-empty, every element in B is an upper bound of L. Well, so anyway, L is bounded above, so now we can apply LUV property on L. So L has LUV property of S implies L has a least upper bound. Say, let's say alpha. Suppose alpha is the least upper bound, so that is alpha equal to supremum of L. Okay. Now we claim that alpha is the greatest lower bound of B. Okay. Now claim one. So first we claim that alpha is a lower bound of B. Alpha is a lower bound of B. So this is claim one, and in claim two we show that this is the greatest lower bound. So first we prove claim one, and the proof of claim one is by contradiction. Proof claim one is by contradiction. So if not, so that is if alpha is not a lower bound of B, then there exists some point B in B such that which is less than alpha. B is less than alpha. So if alpha is not lower bound, so then we have some element in B which is less than alpha. So now what is alpha? Alpha is supremum of, so alpha is equal to supremum of L. Okay, and if B is less than supremum, okay, then B cannot be upper bound of L. That means there exists some element in L. There exists L belongs to L such that B is less than small l. Okay, but what did we say? But we know every element of B is an upper bound of L. By construction, by definition of L, every element of B is an upper bound of L. But here, what we get, B is less than L, where L belongs to L. So B cannot be upper bound of L. So this is the contradiction. So by contradiction, we have claim 1. So also note that alpha belongs to L. Now we have claim 2. We have claim 2, alpha is GLB. If alpha is not GLB, if alpha is, or let's say, let us take some let L be a lower bound of B. Now we show that we show that alpha is GLB. Here, this is the proof of claim 2. This is claim 2. So let L be a lower bound of B. We show that L less than or equal to alpha. Okay, so this is what we need to show. So to show that alpha is greatest lower bound. Now, if L is lower bound of B, so this implies L is less or equal to X for all X belongs to B. And this implies L belongs to L, capital L, by definition. So by definition, so here is the definition of L. So by definition, this small l belongs to capital L, and alpha is supremum of capital L. This implies L is less than or equal to alpha, which is equal to supremum of L. So this is what we wanted to prove. So this completes the proof. So let us stop this lecture.